In this video, we're going to go from acceleration to position in 2 dimensions. I have an acceleration vector function here in 2 dimensions, and we're given that the position and the velocity are equal to 0 at t is equal to 0. We want to find the velocity and position functions of time, and then evaluate the magnitude of the velocity at t is equal to 2 seconds and the magnitude of the position at t is equal to 1/2 seconds. I'm in SI units, so I can say these are meters per second squared for the acceleration, meters per second for the velocity, and meters for the position. My acceleration function, my x component, is given by 6t squared, so it's quadratic. My y component is 4 cosine 2 pi t, so it's oscillating back and forth. If it's not clear what exactly is going on, I have a graph of the y component as a function of time. Cosine itself, the function oscillates between -1 and 1, so 4 cosine oscillates between 4 and -4. The argument of cosine is 2 pi t, and since the cosine undergoes a full oscillation every 2 pi, this function goes through a whole oscillation every second. At t is equal to 1, this is 2 pi. At t is equal to 2, it's 4 pi, so you get one complete oscillation every second. To find the velocity function, we then need to take the antiderivative. And here we need to take the antiderivative of each component. So here's the antiderivative of the x component. T squared goes to t cubed over 3, and then 6 divided by 3 is 2. So I have 2t cubed plus an integration constant, which I call c sub x for the x component integration constant. The antiderivative of cosine of x is sine of x, and then from the chain rule, I have to divide that by 2 pi, so that when I differentiate this and the 2 pi comes out, the pi's cancel, the 2's multiply, and I get my 4 back in the acceleration. So the antiderivative then is 2 over pi sine of 2 pi t. Again, there's another integration constant, which I call c sub y. To find the integration constant, we use the fact that I'm given the velocity is equal to 0 at t is equal to 0. Well, that means each component has to be 0. So 2t cubed plus c sub x must be 0 at t is equal to 0. Well, if I put in 0 in for t, that just tells me that this constant c sub x is also equal to 0. The same thing happens for the y component, because if I put in 0 for t here, sine of 0 is also 0, so for the whole component to be 0, c sub y must equal to be 0. So I can now write out the velocity function of time, which is 2t cubed I hat, the x component is 2t cubed, and the y component is 2 over pi times sine of 2 pi times t. If I want to find the speed or the magnitude of the velocity at 2 seconds, I find the velocity vector at 2 seconds. I plug in 2 for t. That gives me t cubed, which is 8 times 2, or 16, is the x component. If I put in 2 here, I get 4 pi, and sine of 4 pi is still 0. So the velocity vector is just 16 I hat, and the magnitude of that is then just 16 meters per second. I've brought back the velocity function, and now we want to find the antiderivative of this for the position function. For the x component, the antiderivative of 2t cubed is 1/2 t to the 4th. I have t to the 4th, and then divided by 4, 2 divided by 4 is 1/2. And then I have another additive constant, which I call c sub x. In the y component, the antiderivative of sine x is negative cosine x. I've brought the negative outside, and then I have another factor of 2 pi I must divide it by because of the chain rule. And then I have another additive constant, c sub y. To find the constants, I use the fact that the position is equal to 0 at t is equal to 0, which means the components must both be equal to 0. For the x component, that's easy enough because I put in 0 for t, and then I just have c sub x, and if the whole thing must be 0, then c sub x has to be 0. For the y component, it's a little different. If I put in 0 for t here, cosine of 0 is 1. So that means for the whole component to be 0, 1 over pi squared plus this constant c sub y must be 0. and therefore the constant c sub y is equal to negative 1 over pi squared. I can now write out the entire position as a function of time. The x component is just 1/2 t to the fourth. The y component is a 1 over pi squared times the quantity 1 minus cosine of 2 pi t. To see where that comes from, I substituted this 1 over pi squared, factored out the negative 1 over pi squared. So I have a positive 1 over pi squared out here, and then that changes the signs inside, so I have a positive 1 minus cosine 2 pi t. I want to be able to find the magnitude of this vector at t is equal to 1/2. So I first find the vector at t is equal to 1/2. I put in 1/2 for t, and I get 1/32 I hat. And now the y component, if I put in t is equal to 1/2, this now is equal to pi, and cosine of pi is negative 1. 1 minus a negative 1 is just 2, so I'm left with 1/32 I hat plus a 2 over pi squared j hat as the position vector at t is equal to 1/2. Now to calculate the magnitude of that, that's a square root of the sum of the squares of the components, 1 over 32 squared plus 2 over pi squared squared. That second term dominates, but we need both the three significant figures. When I put that into my calculator, I get 0.451 meters because I was told from the beginning everything was in SI.